Hello, everyone. In this video, we're going to look at example 2 in section 6.3. So let's go ahead and read this example together. So we're given a rectangular city having a length of 5 kilometers and a width of 3 kilometers. So we see here's the width and here's the length. And it borders along an ocean as shown in the diagram to the right. So the ocean is here. The population density of the town at a distance X kilometers from the ocean is sigma of X, which is 500 minus 30X squared. And that is people per square kilometer. So at X kilometers in, we should expect the population density to be 500 minus 30X squared people per kilometer squared. And so notice our city, we can think of as two-dimensional. And so that population density is people per two-dimensional unit or people per unit of area. Okay, so now that we kind of have an idea of what the setup is, we want to look at part A. So part A says, where is the population density in the city the greatest? So we want to know, where is this value, this population density, largest? So we can think about what happens as we increase X. So as we increase X, the amount that we're subtracting is going to increase. So the sigma of X, that density, is actually going to decrease. So pause the video, think for a moment of where you might be able to find that largest population density. Awesome. All right, so after you've given yourself some time to think, you may have come up that at X equals 0, the population density is largest. So I'm going to write that down, then we'll think about it. Density is largest when X equals 0. And again, when X equals 0, this term is 0, so we don't subtract anything from the 500. So where is that in our city? Where does X equal 0? X equals 0 right at the ocean. So is that typical? Yeah, maybe. When we are on the coast. Often it is the case that most people in a city that lives on the ocean is closest to that ocean. Okay, maybe not always, but often. All right, now let's look at part B. So part B says, find the population of the city. Okay, so finding the population of the city, if the density of the city was constant, or if there was a uniform density, so say there were 100 people per kilometer squared everywhere, then what we do is just multiply that density, 100 people per kilometer squared, by our total kilometers. So in this case, 30 times 5 kilometers squared. Cancel out the kilometers and we get just 100 times 3 times 5 total people. But we don't have a uniform density in this situation because our density changes as our distance from the ocean increases. So what we're going to do is break up this city into slices or chunks that do have close to uniform density. Okay, so how are we going to do that? Well, we are told that depending on how far X is, so we'll say X is here, then at this little strip, we can make this little strip really tiny, get a little slice though. At this strip, everywhere along this strip has, so we'll call it a slice or a strip, has density sigma of X. Okay, so then what's the area of that strip? Well, we know its width is going to be delta X, and its length is 5 kilometers. And this delta X is also a kilometer measurement. Okay, so let's think about the population in just this strip. So I'm going to say population in slice. Okay, so that's going to be about, so we're going to have our density, population density of that slice, so sigma of x, times the area of the slice. Okay, so what is that for us? Well, the density of the slice is given by our function sigma of x. So we can plug that in. So we have 500 minus 30x squared. Area of the slice is going to be the area of this rectangle. So that's 5 kilometers times delta x kilometers. Okay, I'm not going to include units within that calculation. We'll look at it after. So we just have 5 times delta x. Okay. So if we want to know the population of the entire city, we are going to have to add up all of the slices that we can make in this way. So we want to add all of these up, add all up, and we're going to have our x go from 0 to, well, the end of the city. So in our case, 3, 0 to 3. So we can represent that sum, or adding up the densities of each tiny little slice, as an integral. So our integral will go from 0 to 3. And then our integrand will be that density, or the population of a slice. So that population of a slice is the density of the slice, 500 minus 30x squared, times the area of a slice, so 5 times dx. All right, and so just so we can check units here, let's take a pause to do that. So density is people per kilometer squared, km squared. Our area is kilometer squared. So our total population of a slice is people. And we see that's also the case for our integral. People per kilometer squared. We have kilometer squared. So in total, we get people. All right, so let's go ahead and compute that integral. All right, so I'm gonna multiply that 5 into each term. So I get the integral from 0 to 3 of 2,500 minus 150 x squared dx. Okay, so now I can just take the antiderivative of each term. So that looks like antiderivative of 2,500 is going to be 2,500x. Antiderivative of 150 x squared is going to be 150. Just bring that constant out. X cubed over 3. And I'm going to evaluate at 0 and 3. All right, so now we can just plug in. So we get 2,500 times 3 minus 150 times 3 cubed over 3. And then when I plug in 0, I just get 0 in each term because each term has an x in it. So minus 0. And when I carry out these operations, we're going to get 6,150. And then as we saw, those units will be people. All right, so when you're doing your own problem, I would like to see some work around units. So either include that in your initial integral so that there's consistency with your final units, or include it if you want to show a slice of population as well. Awesome. All right, great work going through example 2.